bijection. So we can say they have the same size. Yeah. Sorry, I was going on autopilot. Okay, it's clearly surjective by construction, since everything in here will be generated by something in there. So this sends H to an element. So did I, when I was specifying the
mapping was from H to GH, and
did I give the rule for that correctly?
Yeah, you gave that.
Yeah, I gave that rule correctly. So to prove injectivity, to consider injectivity, we have to consider the situation that, so the way we should phrase this is that 5H1 equals 5H2, isn't it? Where H1 and H2 are two elements of H. Now, if that can be the case for two distinct elements, two actually separate elements, then the thing will fail to be injected. So we have to, well, meanwhile, we use the definition of phi. 5H1 is GH1, 5H2 is GH2. So yeah, so I just put the indexing, yeah, I mixed up my G's and H's. Again, same thing there. The G's can be cancelled on both sides by P multiplying both sides by G inverse. Put a G inverse on the left here, G inverse on the left there. And so that will imply that H1 is equal to H2, i.e. phi is injected. Yeah? That's the definition of one-to-one. That if two elements have the same value, in fact, they're the same element. Yeah. Yeah, no, that's a good spot. Yeah, I wasn't freewheeling a little bit there. Okay. That's correction to the injectivity part 3. Okay. Now part C. Have you had a chance to think about this? Suppose G is a group of even order. So the order of G is 2 times something. And better be at least 1. I mean, groups by definition are non-empty because they have the identity element at least. So the n must be bigger than equal to 1. Prove that G must have a subgroup of order 2. Okay, this is somewhat related to Lagrange's theorem. I mean, if the size of the group is even, then clearly 2 is a factor of it. So it's not 2 isn't ruled out as being a possible order by Lagrange's theorem. Of course, it's not guaranteed that it has a subgroup just because 2 is a defined. However, this seems to suggest that, well, for the case of 2, it is definite that it does have a subgroup of order 2. So I have a suspicion we might have gone through this in one of the lectures, but I'm not quite sure. So if the order of G is 2n, then certainly Lagrange's theorem does not rule out the existence of a subgroup of order 2. But it doesn't rule it in either. Okay? Lagrange's theorem really just says what doesn't exist. There are no subgroups whose orders are not divisors of the order of G. So, any ideas how to approach this? On the face of it, it maybe appears quite a hard problem because we know nothing else about G except its order. And okay, with the later chapters, when we got into group actions and Seelov's theorem, we did get results that talked about the existence of subgroups, certain subgroups of certain sizes based only on knowing the size of G. But when we were back at the point of first encountering Lagrange's theorem, we didn't have such strong results to hand. Now you could, fact that it has a subgroup of order 2, that would come as an existence, that would come as a consequence of the first C-log theorem. Yeah, if P was a prime dividing the order of the group, then the group had elements of order P. Yeah, there's the first C-log theorem. I don't think it wasn't restricted to be to prime. I don't think. Yeah, so this would be as a consequence of the first C-log theorem, but okay, so such a subgroup will exist as a consequence of the first C-log theorem. That says if any prime power, if any power of a prime divides the order of a group, then, and not necessarily the maximal prime divides, which is divides into it at all, then it will have elements of that. But we can also give a more basic proof of this. Consider a possible subgroup of order 2, possible subgroup H of order 2. Okay, there's only 2 things in H. What are they? I'm sorry, this brings us a bit such bright some data outside of the precedent. So H is a subgroup of 2. At order 2, we're pretending for the moment that such a thing exists. Probably destroy the quality of the data. But what's in H?
The identity.
Good. Certainly the identity. And what else?
It needs another element, but it also needs the inverse of it. So
Yeah.
that element needs to be its own inverse.
Yeah, exactly. There's only space for 2 things. It has to contain the identity. That's good. It has to contain the identity, because it's a group. There's one other thing in it. But it also has to contain all the inverses. Okay, the identity is not the inverse of this. So this must be its own inverse. Okay. Excellent. So H must look like this, where X inverse is equal to X. So the element X is actually of order 2. That's the key insight. Okay, this is just still pretending that such a thing exists. So now we say if such an X, so if we can find an element X of order 2, then the result is proved. As just pairing the identity with that element will be a subgroup. Will be a subgroup of order 2. Okay, I'm adding in some extra descriptions here. You don't necessarily kind of pose all these rhetorical questions in your answer. Okay. Is there such an X? Is there such an X in G? Okay, I've said this, we could claim this result as a consequence of the first C-log theorem, but by implication, there's maybe, in the special case of 2, there's maybe a simpler argument to get to it. That doesn't require all that machinery. Any ideas? So here's G. And what do we know about it? It's got 2n elements, right? So it's got a load of elements in it. Right? Okay, there's an even number of dots there, I suppose. Can I name any one of those dots?
Identity.
Yeah, okay. One of them is the identity.
Also, now there's an odd number, so therefore
Yeah.
one can have a pairing, but it must be one that's self-inverting.
So G less the identity, the order of that is now 2n minus 1. Yeah.
Just
Say what you said again?
just now that makes an odd number of elements,
Yeah.
and all of them must have an inverse, so one must be self-inverting.
Yeah, so so there's an odd number of dots then. The typical situation is you've got an element here, G, and its inverse is over here, a different element. Yeah. But anytime you identify a pair like that, where G is different from its inverse, you're subtracting 2 from this odd total. Yeah. So there'll be another element, H, another typical element, and its inverse is over here. But then that's another subtraction. If you kept taking off those pairs first, what's the situation going to be? Eventually, you're going to run out of such pairs. But you're subtracting 2's from an odd number. So that process is going to, the lowest that can go is going to go to 1. Yeah. But so that process can't end and you run out of elements. So it must get down. So if you identify distinct pairs of G and G inverse, you keep on doing that, but you must be an odd number remaining greater than or equal to 1. And if you've already gotten rid of all the distinct pairs G inverse, all the elements that are left must be self. So there must exist at least one self-inverse element because there's an even number of elements to begin with. If there was an odd number of elements to begin with, then once we've separated off the identity, we've got an even number. So it is conceivably possible that that even number splits into pairs of G and G inverse, G and G inverse, G and G inverse. Doesn't have to, could still have lots of self-inverse elements, but at least it's conceivably possible that it could all be self-inverse. Does a group with an odd number of elements have an element of order 2 inside?
No, because Lagrange's theorem.
Yeah, because that would violate Lagrange's theorem. Because if it has an element of order 2, then this will be a subgroup of order 2. But if there's an odd number, then it can't have such a thing because that 2 does not divide the order. So yeah, it'll be a subgroup of order 2. So so basically, how do we get that idea down on paper in some kind of efficient way? There's just loads of different ways that you might present that idea. Let's say, so G is even order, and if we remove all distinct pairs G inverse, so meaning here, so G is not equal to its inverse from G. This leaves an even number. An even number of self-inverse elements behind. Okay, so take out all the elements from G, or maybe a better way to phrase that, take out all the elements of G of order greater than 2. Yeah, he's going to leave together an even, leaves behind an even number, but the question is, could that even number be 0? Well, no, it can't be 0 because the identity is left behind at least, which is not 0. since E equals E inverse. Of course, the identity is not of order 2, it's of order 1, because E to the 1 is already the identity. So, with the number of so this shows that there must be an even number of self-inverse elements, and it's not 0, so there must be a non-identity element, x. At least one x such that x is not equal to the identity and x equals x inverse. So therefore, as we've explained above, G has a subgroup of order 2. So it's not like we're invoking Lagrange's theorem anywhere there. Although maybe if I would have added on, it would have been a good addendum to that question. If the order G is odd, does it have such a subgroup? Well, then you can say no because it violates Lagrange's theorem. But it's kind of, you know, it's in the same area as Lagrange's theorem, and we noted at the start that Lagrange's theorem does not move it out. But again, it's this kind of, you know, appealingly simple counting ideas, similar to the one, yeah, somewhat reminiscent of the ones involved in the proof of Lagrange's theorem itself, where you're just establishing the partition and then arguing about the total number of elements in G based on counting the D of the partition, if you like. Is that okay? That's good. You had the answer there, Mark. That's good. So, shall we look back to the chapter then on Lagrange's theorem? So this is chapter 6. Not that long a chapter. It basically goes through the definitions, cosets.
Can I ask a quick question
Go.
about this? Does this not prove that there could just be a possibility of a subgroup of order 2, not that there must be?
So here at this point I said pretend there's such a subgroup, just so we could look at it, and so then we clearly saw, okay, the structure it must have is the identity and the self-inverse element. Okay, that's fine. So then we rephrase the question as, can we find such an element X? If we can find such an element X, then there will be such a subgroup of order 2.
Yeah.
Is that okay? So now the task is to find such an X. So now we bring in, now we're making use of this, because nowhere up to, well, we just made the comment about Lagrange's theorem, but we haven't made actual use of this yet. But we do make use of it now because there's an even number to begin with. So if you look at all, so the total number of elements, I mean, there are many different, maybe this isn't the best way of phrasing it. What's the, if you count up all the elements in G, which are not self-inverse, how many of them in total are there?
An even number.
An even number, because they come in pairs, G with G inverse. So you can pair them off, so therefore there's an even number. There's an even number of things in G to begin with. So the number of self-inverse elements, which are not self-inverse, that must be even as well, because we started off with an even number, we took away an even number. But now that still leaves it possible that we've removed all the elements. So there could be no self-inverse elements, except that's impossible because the identity is a self-inverse element. Now the identity isn't the X we're looking for. But now we know that the number of self-inverse elements, which we know has to be even, it's not 0. Therefore, it's at least 2.
Yeah.
Yeah. So there's at least one other element apart from the identity, which is self-inverse. Okay, I can't identify it, you know.
Yeah, I get that.
because- yeah. So does that, so why do you think that doesn't hit the nail on the head and says G must have a subgroup of order 2?
I'm not sure.
Does it still look a bit?
I think what you're saying is because we did start off with like imaginary
Yeah.
as such
Yeah,
start. It's just quite difficult to see the link why there must be that subgroup to the group itself.
okay. Do you accept that there must be such an element X?
If we consider the subgroup H, yes.
Well, see, like, basically, here now you can kind of erase this kind of, this was like a bit of investigation. So, an even number of things in G. There is a even number of things which are not self-inverse because they come in pairs. So therefore, there's an even number of things that are self-inverse.
Oh, yeah, I get it.
Do you get it?
Yeah. Yeah.
See, if there was an odd number of elements in G, there still has to be an even number of elements which are not self-inverse because they come in pairs. But so that means there'd be an odd number of elements which are self-inverse. So that could be the case that there's only one of them, and it's the identity. So then you haven't proved that there has to be such an X of order 2. But in the case where there's an even number of elements, therefore there's an even number of self-inverse elements. The identity is one of them. So therefore that even number of self-inverse elements cannot be 0 because it contains at least the identity. And there must be at least one other, because the next even number apart from 0 is 2. Or
Yeah,
6, whatever.
makes complete sense now.
Okay, good, yeah, okay. But yeah, so maybe, yeah, because in my description there, we had this kind of, so this was just a temporary assumption, just so I could write down such a subgroup. And you see, when you write it down and think of what elements it has, then it becomes apparent, it must have this element which is self-inverse. And so then you go looking for such an element. And any subset that you form like this, with the identity and an X which is self-inverse, that will be a subgroup. It's got the identity, it's closed, it's got all its inverses, it's associative, so it is a subgroup. Yeah. Is that okay?
Yeah.
Good. Okay. Yeah, so in this chapter 6 then we have, he defines cosets. This lemma here, so this featured in the proof here, we proved that the two cosets were either disjoint or equal. This lemma just set up a number of different equivalent statements to the statement that the two cosets are equal. That was just a kind of this just gave him several different versions, well, 5 different versions, different equivalent ways of saying two cosets are equal. And I think he used various of these in the subsequent arguments. Theorem 6.4, he set up the fact that they partitioned the group. Theorem 6.8, he says the number of left cosets is equal to the number of right cosets. Proposition 6.9 is the fact that all cosets have the same number of elements. And then theorem 6.10 is just basically a 1-2 sentence proof, just putting all those facts together, just like then he goes on, he quotes a couple of corollaries talking about this number, the index of the subgroup in G, the number of cosets. And then he does this, this important application to the multiplicative modular arithmetic groups, which we called in last year in number theory Zn, with a multiplication sign on it. He calls here Un, the group of units modulo n. Units in algebra means an element with a multiplicative inverse. These are all the elements in Zn that form the multiplicative group. Zn on its own in this book just denotes the additive modular arithmetic. And the important application here is getting Euler's theorem. That because the order of any element within that group, because the cyclic subgroup generated by an element, the number of things in the cyclic subgroup is equal to the order of the group, so that must be a divisor of the size of the group. Phi of n, the Euler-Toschen function value, that is the size of the multiplicative group. So that's a multiple, therefore, by Lagrange's theorem, phi of n is a multiple of the order of a for any a in the multiplicative group. So therefore, when you raise a to that power, you're going to get 1, because that's just a power of a to the power of its order. And I think last year that might have been I might have proved Euler's theorem by appealing to Lagrange's theorem. This year I actually proved it when I was doing the number theory for students. This year I actually gave so you can prove Euler's theorem just directly in the multiplicative group, so not using the machinery of Lagrange's theorem, but just by looking at the properties of prime numbers and Fermat's little theorem. Fermat's little theorem is a special case of Euler's theorem. And we proved that directly this year. Anyway, but let's look at some of these exercises. Did you get a chance to look at any of these, or no? Okay. Oh, there's an interesting. So this chapter doesn't have a huge amount of exercises, just 23, and it's still pretty big. And there's a few number theoretic ones in the last few questions. And there's several questions kind of investigating certain examples. Well, these just give you test your kind of ability to make some arguments here. So what about that question 1? G is a finite group with an element of order 5 and an element H of order 7. Why must the order of G be at least 35?
Because that's the lowest common multiple to me.
Okay.
By Lagrange's. Both of them have to be able to divide.
And they're both prime.
Yeah. So Lagrange's theorem speaks about subgroups. So what are the subgroups there that you're referring to? So you're right, but just to quote this in terms of Lagrange's theorem. So the element G of order 5, it generates a cyclic subgroup of order 5. Yeah? The identity G squared, G cubed, G4. G5 is already the identity again. Yeah? And similarly, H generates a cyclic subgroup of order 7. So the order of G, whatever it is, well, if it's a finite group, its order is divisible by 5 and divisible by 7. So you're right, the least common multiple of those two numbers, G, must be that size. There is no group smaller than 35 that can have a subgroup of order 5 within it and a subgroup of 7. Plenty of groups that have just a subgroup of order 5 within them. Plenty of numbers less than 25 that are divisible by 5, but none that are also divisible by 7. Yeah, that's correct. And in fact, you could even strengthen this. Not only is G must be at least 35. Can you slightly strengthen that?
Equal to 35 n, pretty much.
Yeah. Has to be a multiple of 35. So it is impossible that it's got size 40. 40 is divisible by 5, but it's not divisible by 7. So that's the principle of the least common multiple. The least common multiple is, by definition, the smallest number that is a common multiple, but it divides all other common multiples, 5 and 7. Just like in a mirror image on the other side of the number, the greatest common divisor is the biggest number that divides into both of them, but it's also divisible by every other common divisor for the other smaller common divisor. So yeah. Okay, that's good. So Some of these are just discussion questions, really. You're happy with that explanation?
Yeah.
Jonathan? Yeah. Question 2. So if you got a finite group with 60 elements, what are the orders of possible subgroups of G?
Any divisor.
Any divisor of 60. All the way from 1, 2, 3, 4, 5, 6, not 7, not 8, not 9, 10. So all the way up to 60. They're the possible. Of course, we're not guaranteed that it has such subgroups. But any subgroups we know are guaranteed?
160.
1 in 60.
Identity in the group itself.
And the group itself.
2.
And 2, because we experienced that today. Yeah. And then with the advent of the Seelof theorems, so which groups would you know existed using the Seelof theorems?
5 and 3.
Yeah. So the first Seelof theorem says any power of a prime that divides the order of the group, it does have an element of that order.
So 1, 2, 3, 4, 5, 15. Oh no, that's not more. No,
15 is the
I'm confused.
pair.
I'm multiples now.
So I think just 1, 2, 3, 4, 5. And they're the only. What is prime factorization of 60? It's 4 by 15, so 4 by 3 by 5. Yeah, so those are the only ones that are guaranteed by the Seelof theorems. There may well be others, but those are the only ones we think we would have at the moment. Yeah. Question 3, prove or disprove. Okay, so those kind of questions. Every subgroup of the integers has finite index. Now, okay, the integers is, so when he just says the integers on its own, he means Z plus the additive group of integers. Remember, the index of H in G is this number, which we call, it's the notation for it, and this is just the number of cosets of H in G. I don't have to specify left or right because there's always the same number. Because you can set up the bijections from the set of left cosets to the set of right cosets. So the group set is infinite, so we can't talk about, the order, we can't talk about the order of a subgroup being a divisor of the order of Z, because the order of Z is infinity. It doesn't have factors. But we can talk about the index, the number of cosets. That might be a finite quantity, or it might be an infinite quantity. So does every subgroup of the integers have finite index? One possible example around this, which I think he discusses in the book, is, so one subgroup you could look at is, say, the subgroup of even integers. So 2Z, which is the set of every even integer, set of even integers. This is a subgroup, closed under addition. It's got the identity, 0 is even. It's got all the inverses, because the negative of an even number is still even. But there's just 2 cosets here. Just 2 cosets. Namely 2Z. And now remember, in the additive group, we use additive notation. So we're not going to write. Yeah, 2z refers to the subgroup, but the coset we're going to write additively. So 1 plus 2z. So that's like the little g, capital H. It's just in this context. Yeah, this is my little g, this is my capital H, but I'm not writing it multiplicatively because I'm using the operation, using the addition notation for this operation, because it is addition. So there it is, just 2 cosets. This is the subset consisting of all odd integers. Yeah, because it's all even integers plus 1. Yeah. So while this is a this is a subgroup of infinite order, it has finite index. Well, I think this is true, except for, so I think the statement holds, and it's kind of the mirror image of the statement in question 4. The statement holds for all subgroups except one. Get to the head mode. Which subgroup is the problem? Which subgroup does not have a finite number of cosets?
The identity.
Yeah, this is good. Is that the subgroup consisting of the identity? The trivial subgroup. Yeah, yeah. Except one, namely second subgroup consisting of just 0. This is the trivial subgroup, just the identity. How many cosets does this have? So what's the rule here? This is where that statement of all the see, what does a coset look like? A coset looks like a little z plus the subgroup. So what's that as a set?
Just a little z.
Just a little z, yeah? So each coset just consists of one element, namely the element that generated. Yeah. How many of these things are there to partition integers?
Infinite.
Infinite, yeah, because they're singleton sets. Have you come across that word, singleton set? This just means a set with one element. Singleton. There's big talk. If you study philosophy, one of the topics you have to go through in philosophy is you have to ponder and examine and discuss the difference between Z and the set containing only Z. And you ponder and discuss whether those are 2 different things or not. Mathematically, we're pretty happy with saying they are 2 different things. This thing here is a set consisting of only one element. This thing here is an integer. Mathematically, we kind of operate the fact that these are different, but it can be slightly confusing. So certainly an infinite number of such cosets. Now this question, is that okay? It's kind of related to question 4. So question 4 says, we got it there. Prove or disprove every subgroup of the integers has finite order. Okay, well that subgroup, the trivial subgroup, certainly does not have finite order. It is order 1. You know? What about any other subgroup of the integers? So similarly, question 4 is false because the order of the trivial subgroup is equal to 1. Oh, sorry. Every subgroup of the integers has finite order. Okay. So it's false because, well, for instance,
Just even numbers.
even numbers, yeah. 2z is a subgroup and it's got order infinity. So it's somewhat related. Still good time. Question 6. Good one. We didn't spend a huge amount of time discussing matrix groups, but they were an important example. Remember GL2R? That was called a general linear group of 2 by 2 matrices with real entries. Now, what was the significance of the general? What? So it consists of every 2 by 2 matrix A. I think N2R was just the notation for all 2 by 2 matrices. But what was the condition for membership in general linear group? N2R was a group under addition. That was an additive group. The general linear group, we want to be a group under multiplication. So what does the criteria for membership of the multiplicative matrix group have to be? Which of the group axioms might cause a problem if you try and form a group under matrix multiplication with all matrices? You can always multiply 2 square matrices, get another square matrix. There is an identity. It is associative, but it's the existence of inverses is a problem. Not all matrices have what we call in linear algebra an inverse matrix, meaning the multiplicative matrix. So you have to restrict membership of this set to the matrices with non-zero determinant, i.e. invert, so matrices that have an inverse. These are sometimes called non-singular matrices. Singular matrix is one that determines zero. So this is the general linear group. So that corresponds to the set of all invertible 2 by 2 matrices. SL2R was the special linear group. Which is a subgroup. GL2R. Do you remember the criteria? This is another. What special value determinant could there be? Probably only one answer.
0. No.
Yeah, it's absolutely not 0. So the only other answer is what other special numbers are, especially in the multiplicative sense.
1.
Yeah. So this is the set of all matrices which have determinant 1. It's a significant subgroup of the general linear group. Geometrically, it has many properties. The linear transformations represented by such matrices are kind of special. They correspond to things that I think preserve length and so on. Well, I'm not quite sure. Anyway, what's the question here? Describe the left cosets of SL2R in GL2R. What is the index of SL2R in GL2R? Okay, certainly GL2R is an infinite group, an infinite number of such matrices. SL2R is pretty infinite too. So what does the left cosets look like? Well, if you let A be an element of GL2R, and A times SL2R is, by definition, just the set of all A times S, where S is an element of SL2R. Okay, well, we've just written out the definition of the coset. What's the determinant of such a matrix? So to start to invest, this is all the membership criteria, the kind of sorting device, the determinant. What's the determinant of such a matrix? If A is in GL2R and S is in SL2R, the determinant of one of those. What's the determinant of a product? Quite an important property of it. Determines the determinant of a product is the product of the determinants. The determinant is multiplicative. So this has the same determinant as A, because the determinant of S is 1. So we wonder, question, is this coset, so you understand this is coset notations like the little g times capital H.
If you move the picture.
Oh, sorry. It's like little g times capital H. The question, is this equal to the set of B in GL2R? Maybe it's the set of every matrix which has the same determinant as. Question mark. Is that true? Well, so suppose the determinant of B is equal to the determinant of A. If we want B to be equal to A times something, what does the something have to be?
I did, like, an identity? No.
It's the identity, then you're just going to get A here. We want it to be equal to B.
Oh, A inverse B.
Exactly. A inverse B. Where is A inverse B? Is it in SL2R? The determinant of A inverse B, the determinant is multiplicative. The determinant of A inverse, what's that? It's like an extension of the multiplicative property. What do you think the extension of the multiplicative property to the
Oh, negative.
nearly like what?
Oh, that's additive.
That's it, yeah, that's it. What's the multiplicative version of that?
1 over it.
1 over the determinant of A, yeah. That's just a general fact of how determinants operate. So you can see this that breaks down when the determinant of A is 0. 1 over 0 makes no sense, but that's okay because A inverse does not exist in that case.
Right.
So it doesn't cause a problem. Yeah. But of course, we supposed up here that the determinant of B was equal to the determinant of A. So therefore, this is 1 over the determinant of A times the determinant of A. So that's just 1. So we're justified in saying this matrix here is an element of the special linear group. So yeah, everything in the coset of A has the same determinant as A. And anything that has the same determinant of A is in the coset corresponding to A, because you can write it as A times something from the subgroup. So yes, the determinant, sorry, the left coset of A actually is equal to the set of, say, X in the general linear group, where the determinant of X equals the determinant of A. So this is the question I posed above, the question mark, but now we've actually proved it.
Could I just have a look at your first line?
Down a bit. That one up there.
Yeah, perfect.
So yes, so the cosets of this, it just stratifies, it kind of like it stratifies GL2R into subsets, all of which consist of matrices all having the same determinant value. So how many of those cosets is there going to be? Finite number? How many different possible determinants are there? 2 by 2 matrices. Yeah, so you can get any matrix. Because this matrix, that matrix has determinant X. So whatever number you care to mention, there's a matrix with that determinant. So there'll be an infinite number of these cosets. So an infinite number of these cosets. So that has infinite index, that's L2 in GL2R. Okay. All right, we've got to finish there for this afternoon.